everyone, this is Ziteng from Cornell. It is my pleasure to share my work here at the Google Federated Learning Workshop. Today, I'm going to talk about distributed estimation with multiple samples per user, sharp rates, and phase transition. This is based on joint work with Jaydev Acharya, Kalem Mankeno, Yuhan Liu, and Himanshu Tyagi. In federated learning system, we are learning based on data from all types of user devices, including smartphones, laptops, and many others. Well, these data are important for federated learning. Due to the growing size of users' data and the model we want to train, getting this data from users might be subject to bandwidth limits. In this talk, we consider the canonical task of distribution learning or histogram estimation in statistical inference and the bandwidth limit. Suppose the data come from a discrete domain of size k, and there is an underlying distribution supported on this domain. There are n users in the system, and each of them observe m IID samples from the underlying distribution. To model bandwidth limit, we consider the case when each user is only allowed to send a bit string of length L to the server. Upon receiving the messages y1 up to yn, the server must output an estimate of the distribution p hat. The error of the estimate is measured by the L1 distance between the estimate and the true distribution. And we want to minimize the error for any worst case distribution over the domain. In the canonical centralized setting, where there is no bandwidth limit, which is L is infinity, the error rate is known to be square root of k over mn. Under communication constraints, the problem has been studied in the single sample setting where m equals to 1. Note that here we require L to be less than log k, since otherwise each user can simply send the observed sample where we goes back to the centralized case. The rate is known to be the following. We can see that the error is increased by a factor of square root of k over 2 to the L compared to the centralized single sample case. However, in many applications, m is bigger than 1. When L is less than m times log k, we cannot send all the samples losslessly. Hence, we must compress the data smartly. One naive way is that each user can focus on the first sample they see and use the existing L-bit algorithm. This will lead to the same rate as before, which doesn't decrease with n, which doesn't decrease when m increases. A central question in this work is that, under a fixed communication budget, can we leverage more samples to get a better rate? To get some intuition, we look at the simplest setting where k is equal to 2 and L is equal to 1. This corresponds to the simple problem of estimating the bias of a coin. Suppose there is a coin with probability of head being p. There are n users, and each of them can flip the coin m times. However, each user can only send a single bit of information to the server. Now the question is, how good can we estimate p? Without communication constraints, using a simple estimator, which just divides the total number of heads by m times n, we get that the error rate is of order square root of p times 1 minus p over mn. This can also be shown to be optimal. However, to implement this simple scheme in the distributed setting, we need each user to send log m bits to transmit the number of heads to the server, which is not possible when each user can only send 1 bit. And it is hard to design a compression scheme for this. Surprisingly, in this work, we showed that under a mild requirement on the number of users, which says that it is at least log of the number of samples per user, there exists an algorithm which achieves this optimal centralized rate. Note that the algorithm only requires 1 bit of communication from each user. Hence, this result is indeed surprising in the sense that the communication requirement doesn't depend on the number of flips each user has at all. At the same time, it also achieves the optimal rate where each user can send the number of heads using log m bits. The algorithm and analysis are the main contributions in the algorithmic part of this work. There are a bit involved, and if you are interested, please refer to our paper. When k is bigger than 2, we can extend this algorithm to the case of general alphabet. We can divide users into k groups of equal size, which we denote as S1 up to Sk. Within group Sk, the users can map their input to whether the data is equal to X or not, which is a binary alphabet. Users in SK can then use the 1-bit algorithm mentioned above to learn PX. Once we do this for every X, it can be shown that this algorithm achieves the rate of K squared over Mn, which is shown to be tight under the 1-bit communication constraint. Note that compared to the case when L is equal to 1 and M is equal to 1, the rate is decreased by a factor of square root of M. This is great. Next, we look at how to extend this algorithm to the general L-bit constraint case. This can be a bit tricky, but here's a naive extension. Similar to the 1-bit case, we associate each symbol with a group of users, and users within each group map their samples to the binary alphabet and learn PX using the 1-bit algorithm mentioned before. The difference is, since now each user has more than 1 bit to send, they can participate in more than one, or more precisely, L groups. Hence, the size of each group is now n times L over K instead of n over K, in the case when L is only equal to 1. Using the same analysis, we can show that the algorithm achieves the rate of square root K squared over Mn times L, which improves upon the 1-bit case by a factor of square root L. However, note that, as we mentioned before, in the single sample case, and L is smaller than log K, the rate decreases as L increases at a rate of 1 over 2 to the L, which is far better than this. This brings out the natural question of, can we do better than the 1 over square root L rate? And hopefully, we can also get an exponential rate. Unfortunately, when M is larger than K over 2 to the L, the answer is no. We show that under certain regularity conditions, the rate scales at most at the rate of 1 over square root n, and the rate can be achieved. This is bad news, which says that when M is large, we cannot do better than this naive reduction. But can we do better when M is relatively small? Here comes the good news. When M is smaller than K over 2 to the L, the answer is actually yes. And we can achieve the exponential rate of 1 over 2 to the L. We also show that the rate is tight by proving a matching lower bound. Due to time limit, we refer to the interested audience to the paper for the detailed algorithm. Note that, compared to the case when M is equal to 1, we improve the rate by a factor of square root M. Here is the summary of our result. Under mild regularity conditions, we obtain tight rates for most regimes of interest up to constant or log factors. The takeaway messages from this talk are, first, more samples help. We can indeed improve our performance when users have more samples, even under a fixed communication budget. Secondly, when consider how the communication budget impacts the performance, there is an interesting phase transition from an inverse polynomial rate to an inverse exponential rate. This phase transition might be of independent interest. Thanks a lot for listening.